Okay, welcome back. Happy Monday. I feel like the weekend just flew by. Today, class number 39. Last project of the semester is assigned and will be collected at the start of the final exam. We're covering something called the fundamental theorem of calculus. Again, it is the fundamental theorem of calculus. It is kind of a big deal. So that's what the plan is for today. Any questions on the calendar? Okay, so let's jump in here at the top of page 62. Daily summary. In this class, we see how to reconstruct a function from its derivative. We also explore the fundamental theorem of calculus, part 1. It turns out there is a part 2. We'll start with number 1. Let f of t represent the value of a stock market investment t months after January of this year. The value of a stock market investment t months after January of this year. That means that f prime of t represents the rate of change of the value of the investment, right? The investment might go up, increase in value, might go down, might lose value. Measured in, let's get some units here. You guys remember the units for a derivative, right? Dependent units over independent units. So what per what? Dollars per month. So your investment might go up $5 per month, and then it might go down $8 per month, right? Always changing, dollars per month. Okay, so here's a picture for us. F prime of t, that's not f, it's f prime measured in dollars per month. So we're gonna use that picture to fill in this table right here together. It says we're gonna assume that f of 0 is $100. That 0 is 0 months, and the $100 is the value of the investment at that moment. So that means we're starting our account by buying $100 of stock, okay? And so right then it's worth $100, then it goes up and it goes down, and we're gonna fill in the value of the account for each of the next 7 months, all right? Okay, looking at the picture, we can see here that in this first month, what can you say about the value of our investment? It's increasing by $20 per month constantly, right? The entire time it was increasing by $20 per month. So for the entirety of that month, how much did our value increase? $20. And so what is the value of our investment at the end of that month? $120. Piece of cake. And then in the next month, what was happening with the way our investment was changing? Constant $20 increase per month. This is easy. What's the value here? 140. Okay, now what happens in the third month? Did our investment gain or lose value in this third month? Gained, but not as much. All right, you guys were really pessimistic there. A lot of you said lose. Just like you had high expectations, I guess. Still gaining, but not as fast. Okay, so it didn't gain $20 for that month, right? It gained less than that. But why is it hard? At least maybe on the surface. Why is it hard to know how much we gained there? Troy.
Because it's not necessarily dependent. It has to approaches.
Mm-hmm.
So we're losing $1.
Yeah. So it's not a constant gain, right? We didn't gain $20 per month constantly. At the start of the month, we were gaining $20 per month. But at the end of the month, we were only gaining $10 per month. And so we weren't gaining anything at a constant rate. The rate at which we were gaining money was changing. Now, 20 and 10, what you want to guess what we actually gained in that month? 15. I mean, that seems reasonable, right? And it's only easy because that is a straight line. That diagonal line is a straight line. But let's talk about really what it is that we are calculating here. What I really want to know is the area under the curve. Let's take a step back. What is the area under the curve here? 20. It is a 1 by 20. The area under the curve represented that rate of increase. What's the area under the curve here? 20. That's, again, the increase. Okay, so this area here is not a nice little rectangle, but whatever its area is, that is exactly how much money we gained in that month. We buy it? It's the same idea. I want us to be thinking about the zombie race. I want us to recognize that this rate of change, this f prime of t, is the same as the velocity curves that I gave you. And just like the area under the velocity curve gave distance traveled, forget about the physics there. It just represented how the position of the zombies changed, right? Forget the word distance, but the area under those velocity curves just told you how the positions of the zombies changed. They were 1 mile down the road, they were 3 miles down the road. It was the way that their positions were changing. Here, the area is just the way that the value of our investment is changing. So we want the area of that thing. Okay, in this case, it's a nice little trapezoid and it's easy, but even if it were curvy, we could play the same game we did before, maybe draw a couple of rectangles and use more and more rectangles, and ultimately, maybe the calculator can help us if it's something difficult. But in this case, it's easy. All right, so the area there is 15. Some of you are embarrassing your high school geometry teachers by forgetting about trapezoids, so let's make sure that we remember the formula for the area of a trapezoid, because this is the shape that we were talking about. Area of a trapezoid equals, let's draw the picture here, there, and there. This guy will be called base 1, this one is base 2, this one down here is called the height. I'm drawing it because most of our trapezoids are going to look like that, but in your high school class, it might have been rotated 90 degrees, and the height would actually have been up and down. Okay, anybody know the formula? Good. So multiply the height by the average of the two bases. That's all. Okay, so let us do that in our example. What is the height of our trapezoid? 1, that's the 1 month, times, and then we're just averaging two bases. What's the first base? I'll call the left-hand side, it doesn't matter though, 20, plus second base, 10, divided by 2. And it's kind of how we did it, 10 and 20, we just took the number right in between, but this will work all the time. Okay, $15 is how much we gained in that month. We were at 140, what are we at the end of the month? 155. Okay, moving on between months 3 to 4. Is the investment gaining or losing money? It is still gaining. That is the shape whose area we want. It is a triangle. It's easy. What's the area of that triangle? Right, 1 times 10 and then half. Right? So 5. So that means we gained $5 more that month. So the value there, 160. Okay, armed with foresight, what should we have done with our stock market investment at that moment in time? Sold. Buy low, sell high. But we did not. We got greedy. We stayed in. And the market was not doing so great after that. So let's take a look at the next piece of this. We've got this shape right here. We want to find its area, so let's find the area. That's a 1, that's a 20, 10. The investment changed by $10 that month. What is it now? 150. It is very natural for us to subtract 10 there. This is the idea of signed area. Anything above the x-axis is quite natural to think of as positive. We were gaining money for the first few months. Anything below the x-axis, you got to think of as negative. If you just asked your calculator, like if you had a formula for this blue thing and you typed in the integral in your calculator and you just went from 0 to 7, that's not going to cut it. We would want to split from 0 to 4, right? That's positive stuff there. And then maybe 4 to 7, that's our negative stuff.
Wouldn't the calculator subtract the stuff that's negative? Is that what we're doing?
It would. As I was saying that, I was like, well, kind of is cutting. It depends on what we're asked to find. What I want to talk about is like what do the numbers really mean? Yeah. But you're right. Yes. I was hoping nobody was going to call me out on that. Thank you, Nick. All right. Let's look at the next picture here. This guy, what shape is that? Trapezoid. Use our pretty new formula for the trapezoid to find the area. Two bases, average them, multiply by the height. What's the average of the bases? 30, right? 20, 40, average is 30 times the 1 month, 30. So we lost $30 that month. What's the value here? on 20. And then finally, this rectangle here, what happened there? We lost 40. Yeah, we were still positive. We were still positive there. So now we're down to 80. Yeah.
That's what you hash it out and put it all on red, right?
All on red. That's right. All right.
Right.
Buy more.
Show demand for the stock.
Okay.
It's gotta stay in now.
We're committed now. All right. Good. All right. So number 3. There is some like high-powered like traders in this room. I feel like a lot of passion. As we've just seen, the area between the derivative, that was a derivative, and the t-axis represents the change in the value of the investment over the course of 7 months. The area under the derivative represented the change in the original function. The original function was f, which was the value of our investment, right? And so we can represent the entire area with this integral. Now I'm using the word area here, but that's not quite what I mean, because we know area is positive, but as Nick says, you know, like in this case, above is positive, but below is negative, so it's really a signed area. So the definite integral there, that whole thing from 0 to 7, represents the change in the value of our investment. We didn't actually calculate the number, but can you look at the, yeah, didn't we lose 20? Like we started at 100 and ended at 80 and we lost 20. And losing 20, we didn't keep track of all these things, but I'm just gonna do it real quick. What's the area of the first rectangle? That's a 20. Next one was a plus 20. The next one was a plus 15, and then plus 5, and then negative 10, negative 30, and then negative 40. And if you do that calculation, which is just the area but with positives and negatives, what do you get? You get negative 20. You can do the calculation if you want to, but it should totally make sense that it's negative 20. And so we are about to connect 2 different things. The area under this curve, which itself was a derivative, right? The area under the curve was negative 20. The difference between the starting and the ending is negative 20, as long as you subtract in the right order, 80 minus 100, right? So what that means is that on the one hand, an integral, the area, is exactly the same as subtracting starting and ending values. And it turns out that's really important. So here it is. That right there is the total area where positives and negatives count just like they should. This is subtracting 80 minus 20, right? But they both represent, sorry, 80 minus 100. But they both represent exactly the same thing. They're both negative 20. And like I said, it's important. In fact, so important it is called the fundamental theorem of calculus, part 1. It says if f prime is continuous on AB, then the integral from a to b of f prime of t dt is f of b minus f of a. Lots of symbols. How much was a in our example? A was 0, bottom limit. How much was b? 7. This guy right here was 80 minus 100. That was the outputs. But the key here is that that is a derivative, and these ones here are original. They're not, okay? So this particular equation, we talked about like nightmare equations chasing you in your dreams. Like this is another kind of one of those, but again, I'm hoping all the pieces make sense. It's got a very special form. Got to make sure you see its derivatives inside the integral, and then original function is outside. Okay, important fact. The units for the integral of f prime of t dt, the final output, are the product of the t units and the f prime units. T units and the f prime units. In our example, what were the units for f prime? Dollars per month, right? In fact, I'll write it this way, dollars per month. What were the units for t? Months. It says the units are the product of those 2 things. What is the product? Dollars. Wasn't it true? The final answer was negative $20, right? And so for me, it makes a lot of sense that the units are what we said. I can see two things in here. There's an f prime. There's a, I mean, it's a dt, but it's got a t in it. So I'm quite happy to look at that and say, oh yeah, that's how I remember the units. It's the f prime units times the t units. Okay, number 6. The rate of flow of oil through a pipe is given by f prime of t equals that equation. Gallons per minute at time t, t is measured in minutes. So this is a rate of flow of oil through a pipe. I called it f prime. Is that a reasonable name? Yeah, it's a rate, right? It's a flow. So we're going to use technology to find the amount of oil passing through the pipe in the first 20 minutes. Let's give it a shot. Okay, so you have your calculator, I've got mine. So first thing I want to see is what this function is doing. So I'm going to graph in the function itself. Make sure your calculator's in what mode? Radians.
Do you not need to put it in parentheses on top?
The x could be in parentheses, but it doesn't need to be.
Oh, yeah, I guess.
You're right, I probably should have put it in just so that it looks like what's written on the paper. Yeah. Okay, so we got our function here. Now before you hit graph, don't just hit graph because the window might not be appropriate. So click on the window. The x min and x max are given in the problem. What are they? 0 to 20, that's the number of minutes. That's easy. But the outputs, not so obvious. It's not obvious what the outputs are. But I could get some sense. If I plug in 0, what do you get? 0 on the top, and then who cares on the bottom. So okay, 0 seems like a good place to start there. And then, I don't know, let's see, 2 plus sign. I mean, it feels like that's always going to be positive, right? So I think we're growing the whole time. If you plug in 20, I don't know, 20 times 2 is 40 over 20. Like it might get up to 5. It's hard to know. Like you could probably just leave it at 10 and see what it looks like. Okay, so that window looks okay. All right, so tell me, is the oil always flowing one direction or is it flowing both directions? Always flowing one direction. All of this is positive. The oil is always flowing in the same direction in this pipe. In the beginning here, the oil is flowing faster and faster, right? Until we get to this point where the oil starts to flow slower and slower, but still in the same direction. And then what happens when we get down to here? Starts to flow faster and faster until we get here, and then slower, slower, okay? That's the idea. It's always flowing in the same direction. What we have seen is that if we want the actual amount of oil that flows through this pipe between 0 and 20, let's write this down here. Okay, what I really want to know, what's going on here? Okay, hopefully this works. What I really want to know is how much is the amount of oil that flowed through at the beginning minus the amount of oil at the start. You guys buy it, right? This is what I'm interested in, is how much oil has flowed through this pipe in the first 20 minutes. F of 20, I don't know what this is equal to. F of 0, the amount of oil that has flowed through, if no time has elapsed, it feels like 0 is a reasonable thing to put there. But how do I relate this thing that I want to the graph that I have? I need to do the integral. In fact, that's what the fundamental theorem says. It says that, hey, if you want to know f of 20 minus f of 0, you just do the integral from 0 to 20. Now, it's really important to put the right symbol. Is this f or is this f prime? F prime. F prime is the thing that's inside that integral. Oops. And that's it. So we've got our calculator to help us, but we just want the integral from 0 to 20, the area under the curve for that picture. So that's what we ask for. Okay, second calc, number 7, 0, enter, 20, enter. Almost feel the oil flowing through the pipe. It's even black, isn't that great? All right, so 27.55. 27.55. Let's get some units here. It's supposed to represent oil, so it better be gallons. But let's make sure that it agrees with what we said before. The units for the integral are always these units times these units. What are the units for f prime? That was gallons per minute times. What were the units for t? It's minutes. And so ultimately, gallons is exactly what we get. So 27.55 gallons flowing through. Now I recognize that the technology is hiding a lot of what's going on here. But this is a complicated problem that the calculator just solved for us. I mean, like it did. I mean, it has to work. Right. It has to. This is work for the calculator. We don't know exactly what it's doing. I'll tell you, it's essentially just doing loads of rectangles, like 1,000 rectangles, which is why it takes a few moments for it to crunch through the calculation. But that's hard, right? This is something like you're driving down the road. Like if I tell you I'm driving at a steady 60 miles an hour, 2 hours later, you can say it's 120 miles I've traveled. But that's only easy because it was a steady 60 miles an hour. Suppose that I was hitting the accelerator like that, where like I'll accelerate for a little bit and then I'll lay off a little bit. And then I'll accelerate even more than before and then I'll lay off. And it's complicated, right, to know how far I've gone when my velocity is changing at every single moment. But it turns out that as long as we can find the area under the curve, it's actually pretty straightforward. Okay. Let's move on to the next page, which is where the activities start. And I will walk around and help.